Hey everyone, so this is going to be the last part in this section of the dynamics unit where we're going to talk about accelerated reference frames. Now, despite the complex nature of the name, it's really not that complicated. An accelerated reference frame really refers to any problem or scenario where an object and the observer are in the same frame of reference and both of them are accelerating. So what's a common example of this? Well, this would be an example of being on a roller coaster ride or a amusement park ride like the Gravitron, where both you and the person in the Gravitron are technically accelerating because you're moving in a circle. And as we talked about, changing direction means that you're going to be experiencing a net force. But if you look at the person, it doesn't look like you guys are moving because you're inside of that same frame of reference, and it's the Gravitron itself that's accelerating. Some other examples, the one that we're going to be using in particular is going to be on the elevator, but it doesn't have to be just an elevator. It could be you in a car. That's another very common scenario where you are in the car. You could have someone next to you. Technically, neither you nor the person are moving relative to each other, but you are in a frame of reference, i.e., the car, that is accelerating. Now, the gist of this and the main idea about these accelerated reference frames is that it's meant to explain some of the things that might make it so that Newton's laws don't seem to hold true. A perfect example is going back to the gravitron. When you go into the gravitron and the machine starts to turn, initially you are standing there at rest, but then all of a sudden you experience a force pushing you backwards. Now, as I mentioned before, we know because of Newton's laws that if we are being forced to move in a certain direction, if there is a change in our motion, there has to be a net force on us. And if we think about it, it wouldn't really make sense because we are not moving inside of that gravitron. Where there's no acceleration inside the gravitron. But because the entire system is moving, because the gravitron itself is moving, that acceleration carries over to me. So even though it may not seem like there should be a force on me, when we take into account the fact that my frame of reference is accelerating, then it kind of makes sense why I'm experiencing that force. Or in the same case of being in a car, if you black out the windows, you can't really tell if you're moving, but all of a sudden you feel a push pushing you backwards. Well, why is that? Well, it's because you're not accelerating, but the reference frame you're in is accelerating, and that's carried over to you. Um, so that's kind of the idea about this. Now, like I said, we're mainly going to be using elevator rides. This is going to be the most common example. So the idea that you go into an elevator ride, and all of a sudden the elevator begins to move, and you'll notice what feels like an additional force acting on you, either a force kind of pushing you upwards or a force pushing you downward. So where is this coming from? Again, it's coming from the fact that the elevator itself is accelerated. The reference frame is accelerated. Now, let's consider a case where the elevator is at rest. You go into an elevator. What are the forces acting on you, and are they balanced or unbalanced? Well, if we look at the scenario, if we're just looking at the person inside the elevator, we know that there's a gravitational force pulling them down and a normal force pushing them up. And because the object is at rest, then that means we know that the two forces have to be in balance because of Newton's first law. For every that an object at rest tends to stay at rest unless acted upon by an unbalanced force. Now, again, if the elevator was moving at a constant velocity, same thing applies because of Newton's first law again, that when an object's traveling at a constant velocity, that the forces must be balanced. So regardless of whether the object is at rest or the elevator is at rest or moving at a constant velocity, the forces acting on us will still be normal force and gravitational force uh, that are balanced. Now let's consider, oh, and this would be kind of the scenario if we draw an FBD. Now, what if the elevator begins to accelerate upwards? Now, what are the forces acting on you, and are they balanced? Well, first off, the forces don't change. We still have a normal force and a gravitational force acting on us. And then if we go back to Newton's law, well, since I am now accelerating and I'm accelerating upwards, then that means that they cannot be balanced, and there should be a greater force pushing me upwards. Now, the real question is, well, what force is bigger and what force is unchanged? Well, in this scenario, it might make sense to say that the normal force has to be bigger, and the gravitational force is the one unchanged because my net force is going up. However, the key thing is while that may be true, that's not really a good reasoning. The force that's unchanged is always the gravitational force because the gravitational force only depends on your mass and the strength of the gravitational force that you're in. Regardless of whether you're in an elevator and the direction that the elevator is moving, you're not changing those two values. Your mass and the gravitational force, the gravitational acceleration of the Earth are independent of the motion of the elevator ride. So the gravitational force, as long as you're on Earth and you're not going significantly far away, will always remain unchanged. Therefore, the normal force is the only force that can be changed, that can become bigger. So the normal force is going to be bigger, not because it's the one going up, but because of the fact that the gravitational has to be unchanged. So the normal force is the only one that can change its size. So again, we just kind of use Newton's laws and say, well, since the elevator is accelerating and the person's accelerating, we experience this force going upwards that is bigger than the gravitational force. All right, so here's the first question. Pause video, work stuff, and we'll go over a second. All right, this is kind of the way that the question gets asked. So here they give us the acceleration of the elevator, and we're told that the person is 80 kilograms. So what I can do is first I can set up my sum of the forces equation because even though I'm at rest inside the elevator is accelerating, so therefore I am also accelerating. The sum of the forces in the vertical direction are going to be the normal force minus the gravitational force equal to ma. I know that the gravitational force is just m times g, so I can pull out an m and just add the accelerations that my elevator accelerating upward plus the acceleration of gravity, and then times that by the 80 kilogram mass, and I get 1600 newtons. Now, what if the object starts accelerating downward? What are the forces acting now? Well, again, no changes. It's still a normal force going up and a gravitational force going down. And the question is, are they balanced? Of course not. Because I'm accelerating, they cannot be balanced by definition of Newton's first law. Now, once again, what force is bigger and what force is unchanged? Well, as we mentioned, your force of gravity, your weight, never changes as long as you're not going, to a different planet. So that, as long as we're staying on Earth, that force remains the same. Therefore, again, the force that changes has to be the normal force. So while the gravitational force is now going to be the bigger force, it's not because it became bigger, it's because the normal force became smaller. So again, in order for you to accelerate downward, this force has to be bigger. But again, I can't make this bigger, so this one has to get smaller. Now, one thing to keep in mind is I mentioned before about how you're going to have to draw FBDs, and one of the concepts is that you have to make sure that the lines length represent their relative values. So if you were being asked to draw an FBD on a person in an elevator while the elevator is accelerating upwards and downwards, one thing that you would have to make sure that you show in your FBD is that the force of gravity did not change in those two scenarios. That the force of gravity was always, let's say, 2 blocks down. Uh, but you would have to make sure that the normal force was changed and changes their size in order to make sure that the acceleration is going in that proper direction. If it's accelerating up, you want to make sure that this was bigger than the 2 blocks. And if it was accelerating down, then this was smaller than 2 blocks. All right, so here's another question. Pause video, work itself. We'll go over in a second. All right, so here we have the elevator accelerating downward. Basically, we do the same thing, but this time I flip force of gravity and the normal force because, again, the direction of positive is direction of the acceleration. My acceleration is down. Therefore, the gravitational force that's going down is now positive. Again, move things around, plug the numbers in, and this time we end up getting a 0 Newton force, which kind of makes sense because if the elevator is accelerating downward at 10 meters per second squared, that means it's basically in free fall. The elevator's in free fall, I'm in free fall. Technically, I'm not touching the floor. The floor only happens because it's resisting me from going down further. But if the floor is falling down at the exact same rate I'm falling down, well, it's impossible for me to apply a normal force on it. Therefore, the normal force will be just 0. So that was a video that you can watch that kind of shows this idea of accelerated reference frames. In fact, going back to that video, that's kind of what's going on in the ISS. If you actually think about it, if you go to the ISS, if you've seen videos, you've noticed that the astronauts are always kind of floating in midair, and it looks like there's no acceleration, no gravity at that point. But that's not true. Technically, there is gravity because when you go to that height, you're not that far away from the Earth. In fact, if I recall correctly, I think the gravity actually only drops to about half of the Earth's gravity by that point. Not even half. In fact, you technically would experience gravity all the way to the moon. The moon is being held by Earth's gravity, so the gravitational field of Earth extends really far out. Technically, it's impossible to get to a point where the gravitational field is exactly zero, but you get to a point where it's essentially zero. However, why are the people floating in midair when technically there's still a gravitational force on them? Well, it's because both of them and the ISS are in an accelerated reference frame. They're technically both in free fall. The ISS is constantly falling towards the Earth, and that's actually what an orbit is. They're constantly falling to the Earth, but they're falling so slowly, or they're moving so fast in its orbit that the Earth basically has time to kind of curve away, so it's constantly kind of missing the fall. Uh, while the ISS is doing that, you are also in that exact same orbit. You are also technically constantly in free fall. Both you and the ISS are in free fall the entire time. So you never apply a normal force onto the ISS. Therefore, you feel weightless. You feel as if there's no acceleration. And that's kind of the idea, again, about the whole accelerated reference frames, that the laws of physics seem to kind of not make sense until we take into account that whatever object we're in or whatever frame of reference we're in is technically accelerating. And then that would explain the changes in Newton's laws. You know, if you start throwing a ball in the air and you see the ball veer off in a certain direction that doesn't seem to make sense by the laws of physics, it's because of the accelerated reference frame, that there's something else going on. So now I should have said this in class at some point, but the scale that you stand on, reads what's called your apparent weight. It doesn't actually read your actual weight. What do I mean by apparent weight? Well, think about it like this. If you stand on a scale and you push someone down with your hands, does the scale reading go up or down? Well, you should know that if someone pushes you down on the shoulders, the scale reading goes up. But technically, your weight, the actual weight of you, has not changed. What has changed is how much force you're applying downward. Your weight has stayed the same, and therefore, when the scale reading reads it, it's reading how much you're pushing down on it, which is your apparent weight. The reason why this is important, and therefore it's reading your normal force. The reason why this is important is because of the fact that uh, when they ask these questions about the elevator ride, they're going to mention apparent weight. They're going to mention the scale reading weight, and the idea is that you cannot relate the scale reading to the person's actual weight. The scale reading is just reading your normal force. It's reading what it seems like you weigh. All right, so here's a perfect example. So pause the video itself, and we'll go over in a second. All right, so we have a man standing in an elevator. He looks down and the scale reading is 200 newtons. So first question is, what direction is the elevator accelerating in? If we look at it, the person is 95 kilograms, which means that he has a weight of 950 newtons downward. Now the scale, which is the normal force, is 200 newtons upward. Because the downward force is greater than the upward force, we know that the elevator has to be going downward. So what's the magnitude of the elevator's acceleration? Well, since the gravitational force, because it's going downward, we know the gravitational force is the one that's positive. So we use our F net equals ma equation. We subtract the force of gravity and the scale reading's normal force, divided by the mass, and we end up getting 7.9 meters per second squared. Now the next question is the elevator moving upwards or downwards? And the answer is, we don't know. There's not enough information. The reason we say this is because of the fact that we only know the direction of acceleration. technically the object can be moving in either direction. Because remember, velocity and acceleration are not the same thing. They're related, but not the same. Meaning, the elevator could be moving up and accelerating downward, which means it's slowing down. So maybe it's going to the top floor, or it could be going down and accelerating down. So maybe it started at the top and is now kind of starting its motion downward. So without any more information about at which point in the elevator ride this person is, whether the person's in the just starting the elevator ride or just ending the elevator ride, we cannot determine the direction of the velocity. And this is extremely important. Just like how you can't determine velocity based off just a normal FBD, you can never tell whether an object is moving at a constant velocity based off the FBD for the most part. You can't really determine direction without more information, without things like friction or knowing what type of velocity it's starting with, yada, yada, yada. So we would need something more before we can continue. All right, so here's the next question. Pause the video, work itself. I'm going in a second. All right, so we say we figure out that the person measures their weight. It's 500 newtons, and this is before getting on the elevator. So we can tell that this is going to be the normal weight. This is the actual FG value. And then it says while the elevator is moving up to the eighth floor, his weight was measured to be 600 newtons. And they want to know what the magnitude and direction of his acceleration is. Well, now that I know this, what I can do is set up my FBD and my whole sum of the forces equation. So we have because he's this 600 newtons is the bigger one. We could do 600 minus the 500 equal to ma. The mass is just going to be 50. So we end up getting 2 meters per second squared up. And this will be the last question. So pause video, work itself. I'll go over in a second. All right, so we have a dog that weighs 500 newtons at rest, goes into an elevator, and the elevator is accelerating upward at 9.8. What is the scale reading? Well, again, we do our sum of the forces equation. The normal force, because it's accelerating upward, the normal force is going to be the positive one. So we move FG over to the side, get it, and we end up getting 1,000 newtons, which kind of makes sense because if you're accelerating upwards at the same rate of the acceleration of gravity, it basically does double duty and you end up doubling your weight. All right. And that's pretty much it for the elevator rides and the accelerator reference frames. Like I said, it's really not that complex. Now, this isn't the end of forces in general. What we're going to end up moving over when we get to Unit 3, we're going to talk about some of the more unique forces. We're going to talk about the horizontal and angular projectiles that were from Unit 1, as well as what's going to happen when we start looking off into planets and we start talking about the big gravitational force equation, circular motion, and planetary motion. Uh, so that's it. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.